I think in the last 5 lectures or four lectures, I covered all the fundamentals of crystallization, and then we talked about driving force. In this case, it's supersaturation, and we also defined the supersaturation ratio, like C by C star. And then I talked a bit about metastable zone width. I showed the diagram. We also talked a bit about the solubility, and then I also showed how to identify the process conditions where we can control the crystallization process. And then I also talked about what's nucleation, crystal growth, and obviously both of them we use it for the same reason. We can go for nucleation or we can just stick to crystal growth, but the ultimate aim is to purify something. So we already saw the basics behind nucleation, and also we covered yet a little bit about crystal growth. So we will study about this process a bit more in this lecture. And then finally, I also talked about nucleation and I explained how it works at molecular level. We also derived the very famous Gibbs theory. And then coming back to the topic of crystal growth, I think I explained you already when we should think about growing the crystals without introducing nucleation in the crystallizer. So I said there are nucleation is extremely good. We can use nucleation to purify a compound, but it comes with its own limitations, which is the crystal size distribution, and then we don't know what's the number of crystals inside. If you don't know the number of crystals inside, which mean you can immediately claim the fact that we do not we can call at least like it's not anymore a controlled crystallization. So controlled crystallization means you can control the crystal size distribution. You will know at any moment during the course of crystallization the number of particles inside your crystallizer. So you don't have to predict anything. Like there are few techniques that allows you to get some rough idea about the crystal population. We call them as population balance model. But okay, for this module we don't have to worry about that. But keep this in the mind, like whenever I say, or the industry people, they say it as control crystallization, which mean they can control the crystal attributes. One is the size, the shape. Apart from that, they can also have some information about the number of particles in the crystallizer. There are few ways to calculate that. Maybe I will cover at the end of this video. Maybe I will talk a bit about 10 minutes on how to get the number of crystals based on the mass of crystals that we add into the crystallizer. Or maybe after this video, during the tutorial time, I'm planning to create maybe 5 to 6 problems in the field of crystallization, so which they may be like exam type questions. So that time I will show you how to get the number of crystals. Like for example, you know the average size of your crystals, and then imagine you weigh like 1 gram of some crystal. Then from that, there are there are some empirical ways to get the number of crystals. So we will come to this topic maybe during the tutorial time, but for the moment, just get the idea what's meant by controlled crystallization. That's a must. And then I'm going to I want to say a few more important reasons, like why we go for crystal growth process. In the previous lecture, I said the main idea are the industry people, they like to go for crystal growth, especially when they need larger crystals, which mean they can easily filter the final crystals, and then the drying becomes easy, and also the flowability becomes much better when you have a larger crystals. But apart from that, there are really very important reasons that can save the life. So and I'm going to list two of those reasons, so that from that you will get some idea. So one main important reason is controlling polymorphism. So uh, so what's mean by polymorphism? Polymorphism is something like you few molecules can crystallize, but it can crystallize into more than one crystal structure. So polymorphism is something like you imagine you have a molecule, it can crystallize into more than one crystal types. So we call them as polymorphs. I try to draw some diagram, like a two-dimensional diagram, so that might get you some idea. So just imagine this is a, let's put some highlighter. Just imagine this is one molecule, this is another molecule, and just imagine these two molecules, they are going to come together and they get crystallized. And for the moment, just think this molecule is composed by two atoms. One is red color dot and another one is blue color dot. So they can come together and assemble something like blue goes to red and red goes to blue. So that's the interaction pattern. So something like here. So blue goes to red, red goes to blue. They can assemble in one form. Imagine if this is a crystalline structure. So we can call this as form 1. This is crystalline, and that which we get from the, which we can make from the, this molecule that contains two types of atoms, blue atom and red atom. And just imagine this can assemble into different pattern. How do you call, the assembling pattern can change, but still it will follow the rules of chemistry. Red goes to blue, blue goes to red. So, and this will be, say, maybe an elongated crystal. So this is another way the crystal can crystallize, or sorry, the molecule can crystallize. So we can give the name form 2. So if the same molecules, if it can assemble into different crystal structure, we call such type of system, or the process as polymorphism. So this is polymorph 1 and this is polymorph 2. So that's the easiest way to explain this phenomena. So why we are talking about this? Because I said, I already talked a lot about nucleation, and also when we go for nucleation, when we go for crystal growth. But in the industries, if imagine like if we just form 1, if this is the one which is going to do the job, yes, says it's going to cure some disease, and this one, it don't doesn't have any therapeutic potential, or maybe their bioavailability may be poor, then we have to crystallize just the form 1 crystals. So in that case, crystal growth is the only option. No, no, it's not the only option, but is the is the easiest option. And also I will tell why is that. So crystals, it's still a mystery, but crystals behave in certain way. Like, let's go to this topic, control polymorphism. So i I already showed you how to create a supersaturation. So we take a reactor, we make the supersaturated solution, and then we add a bit of some small quantity of crystals. So the plan is to, we are going to grow these crystals in the supersaturated solution. So if this is our experiment, if we are going to add, say, form 1, and this is completely solution, say this solution is made up of this molecule that contains two atoms. So, and if we add form 1 crystals, we will grow only form 1 crystals. So that way, at the end of your experiment, you will just get form 1. It will be a bigger sized form 1 crystals. So this is one way to get only one form of your molecule, of your target compound. This way, the first thing, you control the crystal size distribution, and the second thing, you also control the form of your final crystal, or which means you dictate the crystal structure of your final crystals. So this is such a cool experiment to do, and that's why industry go for crystal growth process. So whenever they want to crystallize a particular form of a target molecule, then they will go for a crystal growth experiment instead of nucleation. If they go for nucleation with this type of molecule, at the end of your experiment, they might end up with any one of these form 1 or form 2. So there are two possibilities. Yeah? So if they get form 2, then they have to dissolve back and do the experiment again. If they get form 1, which is well and good, and there are some cases where they can get both form 1 and form 2, then life will become even more difficult to separate them. Yeah, so that's why they will go for crystal growth process to control polymorphism. So I hope you all follow this one. These are really important, especially I know this class is, we have almost 80 percentage of the students, they are from pharmaceutical chemistry, and they should know all these basics. And crystallization is you should study in detail when you compare to other topics in the module, because I really believe crystallization and chromatographic techniques, these are going to save your life if you're going to get a job in companies, pharma companies, sorry. And then what else? And then crystal growth becomes handy when we are going to deal with chiral compounds or chiral molecules. I hope you all know enantiomers. It comes from the Greek word enantios, means opposite, and mers or meros. Sorry, I wrote it here. It means parts. So it means opposite parts. So what do I mean by that? I know that I know most of you know what's mean by enantiomer. Anyway, I will just say it quickly. So you take one molecule and you take the mirror image of the other molecule. So sorry. If you want to put it simple, so enantiomers are some to be simple, enantiomers are just chiral molecules. So that are mirror images of one another. Yeah? So how to draw it simple? Imagine if this is your one molecule, you have the mirror image of the other, sorry, mirror image of the same molecules, and they both can crystallize. Just imagine they crystallize something like that, and then this one, it will crystallize something like that, and they both will have a different crystal structures. And imagine only one of them produces the desired physiological effect, while the other one may be inactive. So in that case, you need to crystallize or selectively crystallize only this type of or this form or maybe exactly this part of the enantiomer. Yeah? So in that case, if this is your final objective, then we must go for crystal growth. I think I made some diagram in the next page. I just put some example. I know everyone in this classroom knows what is a chiral compound. So here I just put lactic acid. This dotted triangle means this is behind the plane of the paper, and this filled triangle, it means it's coming, how do you call it, it's popping out from the paper. So that's why this is the notations used by chemistry people. That's how they draw the three-dimensional object. on a two-dimensional paper. So if you see here, the hydroxyl group is on the right hand side, and in this one the hydroxyl group is on the left hand side. Normally they give this notation D if the hydroxyl group is on the right hand side, and they will give this notation L if the hydroxyl group is on the left hand side. So, and they both will crystallize into different crystal structure, and maybe one of them will produce the desired physiological effect. I think I have some few examples. So what will be the idea? Yeah. So and one more thing, you should know what is a racemic mixture. So racemic mixture is something like you have some mixture, while 50 percentage is this part of the enantiomer, and the remaining 50 percentage is this part of the enantiomer, like exactly 50 plus 50. So we call them as a racemic mixture. Some in the text, some textbooks they also call it racemate. Oh, changed pen. Racemates. So these are basics. So again, why are we talking about this chemistry? In fact, it's not necessary for this module, but why we are talking is like, if you want to crystallize only this part of the material, then all we need is to make a supersaturated solution, and then you have to seed the solution with this type of crystals, this part of the enantiomer. So crystals composed by this part of your enantiomer, say D-lactic acid. So if you seed the crystallizer with the D-lactic acid, then you are going to crystallize only this type of structure. So that's the key idea behind the crystal growth. So these are some of the key advantages of using crystal growth instead of nucleation. If you cool down the supersaturated solution, and if you wait for, and if you go up to the metastable zone with, and you allow the system to nucleate, then you might end up with any one of these enantiomer, or maybe you might end up with a racemic mixture, 50 percentage of one part of your enantiomer and 50 percentage of the other part of your enantiomer. So nobody likes that. So let's go a bit more into the topic. And why do we need to crystallize only one part of your enantiomer? I put some example. I know for if pharmaceutical chemistry students, they might have studied this in some other module. I'm not aware of that. So only one enantiomer can give the desired physiological effect. If this is the case, it's better we crystallize only that part of the enantiomer. Yeah, why not? So and the other second enantiomer may be inactive, and sometimes it can even produce adverse effects. So which means we shouldn't have even a tiny percentage of the second enantiomer in the final product. I'm sure many of you might have known this one, Zopi Clone. I don't know how to pronounce. If my pronunciation is not correct, forgive me for that. The Zopi Clone is a racemic mixture. Exactly, it contains 50 percentage of D and 50 percentage of L form. So out of this, only one form is active and other one is inactive. And how do you call this? Is called Zopi Clone. So this is a single enantiomer that contains only the active part. So only the active form, which means this is a, by the way, this drug, we use it to treat insomnia. Everyone, at least most of the people have this one, including me. So what does this mean? Like if you manage to crystallize only the active form, so then we can reduce the dose. Like for example, we have to give Zopi Clone, say like 1 milligram, but this drug we can just give 0.5, exactly half of that, because this 0.5 contains 100% the active form, the 100% the active drug, whereas this one only 50 percentage of the drug is active. So that's these are some good reasons, and if you want, we can call it like the the motivation behind the crystal growth process. This is extremely important. So that's why for your lab, I designed this crystal growth experiment. Okay, what we did in the lab is we used a normal API, which is a paracetamol. And so what we are going to learn through this experiment is like how to perform that crystal growth experiment. We are not going to deal with a racemic mixture, or we are not going to deal with a polymorphic transformation during the crystal growth process. We are going to take a form 1 paracetamol, and then we are going to grow that crystal from in the supersaturated solution. And by this way, I think you already learned almost all the essential topics in crystallization. I think if we fairly covered this topic. I, I think it's more than enough. If you get a job in industry and by chance you become a crystallization scientist or a pad scientist, I think you learned more than enough from this module, especially from this chapter, crystallization, and also from the experiment which deals with pad assisted crystallization. In the lab, we performed crystal growth experiments. I think only now we are going to cover the real topic about your laboratory experiment, yeah, that deals with crystal growth of paracetamol. And then we monitored the whole crystallization process using pad tools. So normally, as they call in industries, we can call the title of your lab experiment as pad assisted crystallization. And the main motivation, obviously, you should know everything about pad tools and what it can do and what are the key advantages of pad tools. Apart from that, from the crystallization side, you must know how to perform a crystal growth experiment, and not just a crystal growth experiment. You should know how to perform a controlled crystal growth experiment. And I already said why do we need to perform a controlled crystal growth experiment. So there are so many good reasons I already explained. And obviously we can do a nucleation experiment. In fact, nucleation experiment is extremely simple. We don't need a pad tool or anything. All we need is to know your solubility, and then if you have this metastable zone with line, you create you come to this metastable zone with, and then you just wait until all the solutions nucleate. So you can start with the different supersaturation, say like supersaturation 4, 3.5, supersaturation 5, 6, 7, 8. This can be slightly above the metastable zone width. Why not? And then you wait, and then everything will nucleate eventually. So, but the key disadvantages is like you will have a big, broader crystal size distribution, and then if you're dealing with like enantiomers, then you might end up with Rashmic mixtures in the as your final product, or you may end up with a polymorph which you don't want to use. So these are some disadvantages. So that's why we decided to go for a controlled crystal growth experiments. And apart from that, from the theory, or if you listen to the part 1, part 1b, I think part 1a to 1d, if you listen to all these lectures, you would know how to perform a controlled crystallization experiment, and then how to exploit this graph, this crystallization map. We know how to draw the line. We can pick some condition, and then we know that's the safest supersaturation for my compound, and then you can perform a seeded crystal growth experiment. Yeah? So I will explain it what's mean by a seeded crystal growth experiment, and that's what we did in the lab. I'm saying that we did in the lab because you are going to write the experiment assuming that you did that experiment. Yeah, obviously, if if the situation is normal, I would have taken you to the lab while I was doing that experiment. So just to think you did the experiment. Yeah, I just only assisted you. and you are the one who integrated the pad tool into the crystallizer, and you are the one who did the experiment. So that's how it works. So, and we know how to perform a controlled crystallization experiment. And and why I am saying why we selected this experiment, or why we are learning this experiment, is extremely important, and it's widely used in food and pharmaceutical industries. So if you don't believe me, you just open any sugar packet that you have in your home. If you have brown sugar, it's even better. If you just spread the crystal in maybe in a piece of paper, or maybe some chart black paper, if you spread those white crystals, you will see all those crystals, they have extremely like a same size. You won't see the size distribution. Even with your naked eye, you can see that all the crystals have similar size, and that's because those crystals were grown using the crystal growth approach instead of nucleation. So that's the main purpose of studying this experiment, or how do you call, like, that's the main purpose that we did this experiment, because industries, they prefer to go for crystal growth for many good reasons. Yeah. So let's go to the crystal growth experiment that we performed in the lab. So what we did is, like, we performed two experiments, experiment 1 and experiment 2. So these are the conditions. If we want, we can call it as experimental conditions. So we added 76.04 grams of paracetamol. So this is like your initial condition. So if you want, we can call, like, this will be your concentration of your paracetamol when time t is equal to 0. And I used a reactor of 1 liter or 1000 milliliter. I used a reactor of 1000 milliliters, but my reactor volume is only 750 milliliters. So take a note of this one. So my reactor volume is just 750 ml, and my solvent is, I used isopropanol. Shortly, I used the acronym like IPA. IPA means isopropanol. And these are some data which I already know. The solubility concentration of paracetamol in this solvent, which is isopropanol, at this particular temperature, which is 20 degrees centigrade, is roughly 108 gram per kilogram of IPA. So that's your solubility. And then we performed all the experiments at 350 RPM. So how do you, maybe I can draw the diagram. So we have some reactor, and then we have an overhead stirrer. So we agitate this solution using some, we used a pitched blade impeller. I can add the photograph of the impeller which I used, or if you want, you can see it in the YouTube videos. There I showed what type of impeller we used. So we used the pitched blade impeller. It has 4 blades. So that, and then we provided agitation using the overhead stirrer. This is connected to some motor, and all the experiments were performed at a constant agitation speed of 350 rpm, which means 300 revolutions per minute. And then this is our working temperature. So we are going to grow the crystals at 20 degrees centigrade. And then we used these 3 pad tools, FBRM, FTIR, and then PVM. So PVM is to check, or to capture the images at micron scale. FTR is to monitor the concentration. And then we used FBRM to track the particle counts plus the particle size. So it's for dual purpose. It will give something or some information about the number of particles, and also the size fractions. number of particles under each size fractions. And then more experimental conditions. So for the experiment 1, our seed loading is 50 percentage. So we will come back to this. What does that mean by what do I mean by 50 percentage? And then we used a seed size of 180 to 200 microns, and I already got these crystals. I performed some nucleation experiment. I filtered the solution. I take the crystals out. I dried them, and then I did some sieve, and I used a sieve shaker to so this one refers to the crystals obtained using the sieve shakers. So whatever this number 180 to 200 microns, so these numbers refers to, to the sieve plates which I used. So my average size of my particles of or average size of the seed crystals, it will be something in between. It will be around 180 plus 200 by 2. So whatever the number you get, so 380. It will be 190. It's obvious. This is approximately your seed size are 190 microns. Micrometers or microns, both are same. And then if we go to the second experiment, so this is our first experiment, and then the second experiment, I maintained all the conditions, everything is same, but the only difference is this time I used 80 percentage seed loading. So that's the only difference between these two experiments. And then, so these are your experimental conditions. Take a note of these things, and then let's go to the next one. So what you need to do, so I'm going to give you the following data. So that's why I put like given experimental data. I already converted the spectra into concentration, FTIR spectra into concentration. So what you need to do is like, you will have some data like this. You will have time expressed in minutes, and then next will be concentration of your paracetamol in the solution. So at 0th minute, what will be your concentration? At minute 2, what will be your solution concentration? Minute 10, what will be the solution concentration of paracetamol, or concentration of paracetamol in the solution. So these are the data we obtained from FTIR, and then I will give you the number of particles under each size fractions. One will be less than 10 microns, another will be 10 to 100 microns, and third one will be 100 to 1000 microns. So all this information we get through FBR, and then I will also, by maybe I will send one word file to get with some PVM images, the images that we captured using PVM, just to show like what type of images we can capture using PVM, or how the image quality will look like if we take all those. I mean, how the image, how do you call like the PVM, we are we are capturing the images directly from the solution. So you cannot, the optical resolution will be, you have to compromise with optical resolution, but still you can see the shape of the crystals, the size of the crystals. If you want, you can even measure the length of the crystals. Yeah, like you can imagine, if this is a frame, if you have one crystal, two crystal, you can draw a line and check the length of the crystals if you want to manually interpret. So these snapshots will give some idea about what will be the resolution of the images that we get from PVM technique. So what you are going to do is like, you are going to make use of all of this data, and then you need to plot. You need to work a bit. So what we are going to plot is like, you are going to plot the supersaturation ratio versus time. Time will be time will be expressed in minutes. So time will be in the x-axis, and your supersaturation ratio, this will be on the y-axis. And then you have two experiments, so you have to plot both. You have to plot the, so let me change to highlighter. So this first one, this one will be the results from the 50% seed loading, which is your first experiment. And then the second one, this one, follow the blue highlight. So this will be the results that you obtained from the second experiment, where you used, or where your seed loading is equal to 80%. So we will come back to this, what's meant by 50 and 80. I will show you how to calculate. And then, so this is your figure 1. So this is your figure 1, and then this will be your figure 2. So you will have, this is your second experiment, 80% seed loading, and then this is your first experiment, 50% seed loading. But this time you are going to plot something different in the y-axis. In the x-axis, it will be time expressed in minutes or seconds, whatever the unit you can use. But in the x-axis, we are going to use some value. It's called delta C. So what is this? So delta C, this is something like your your concentration minus your solubility concentration. So this is the value you are going to plot. So the unit concentration is expressed in grams per liter minus grams per liter. So whatever the value you get, that will be in grams per liter. So in this one, the figure 2, you have to plot delta C expressed in grams per liter versus time in the x-axis. So what does this graph mean? It's like, so by this, at this end point, which is somewhere around here, so that will be the maximum amount of mass that you can crystallize in 1 liter of your solvent. So this one will give some rough idea about this one. And if you see this line, let's change to, okay, the pink highlighter. So this, so this one gradually increases with respect to time, which is okay. But when you compare it with the 80% loading, so you see the amount the amount of mass that we crystallize in that 1 liter of your solvent, that increases even more faster. So that's the benefit of using higher seed loading. Yeah? And it's the same if you come to this type of graph, supersaturation versus time. What you can see is like, you have 50% loading. You see the supersaturation is consumed very slowly when you use a 50% loading. But when you use a 80% seed loading, the supersaturation will be consumed more faster, which means we are speeding up the reaction. So that's speeding up the whole crystallization kinetics. Eventually, your supersaturation ratio will come to value of 1. Yeah? So this is something like 1 to 1.2. I will tell what these numbers mean soon. And then this is your figure 3. Figure 3. So all you're going to plot is like number of particles in the y-axis. So it has no unit. This is just a number. And then time expressed in terms of minutes. And that's time on the x-axis. And then you have to plot 100 to 1000 microns. Another line will be less than 10 microns, and some numbers that corresponds to 10 to 100 microns. If these numbers are constant, that means it's called controlled crystallization, because we maintain the numbers to be constant, which means there is no nucleation. If you have a nucleation, then it will give rise to millions and millions of new particles or new crystals in the solution, but we are performing a controlled crystallization experiment like the industry people they do. So that's why this number is going to be constant. So based on this graph, all you need to say is like, okay, this graph shows some information about the number of particles under each fractions, and to me it looks like the number remains constant throughout the experiment. So which means I the experiment is well controlled, and then there is no chance of nucleation. So whatever the number of particles I added, it remains same, and only they are growing. Yeah. So if you added the 1 million particles, it's going to be 1 million particles at the end of the your experiment, but probably their size will be different because you are growing them in the supersaturated solution. So your figure 3 will be for 50% seed loading, and then your figure 4 will be the same plot like figure 3, time in the x-axis, number of particles in the y-axis, and then again the three different size fractions, and based on that you have to write if the lines are constant, which means it is constant. I already gave some explanation in the YouTube video about this data. I think I talked a bit about how the number slightly increases and some size fractions they remain constant. So these are the ideas these are the things you should include in your report. And then finally you have to do some mathematical calculations. So you need to calculate one more parameter. So you have to calculate the amount of paracetamol or amount of mass transferred onto unit mass of seeds. So what do I mean by this? So imagine you have a crystallizer, you have a supersaturated solution, and then once you add say like 3 crystals for the moment. So since you have a supersaturation, your paracetamol will go from solution to each of those particles. So what we are going to, and we know the, let's say this mass of these 3 particles is say 1 gram, and let's say some mass say like one molecule goes here, one molecule goes here, one molecule goes here, or maybe say 1 gram of paracetamol go and attach to this particle, 1 gram of paracetamol go and attach to this particle, and 1 gram of paracetamol is transferred from solution to this particle. So which means we transfer totally 3 grams of paracetamol. So 3 grams of paracetamol divided by this 1 gram of all these the seed particles that we added. So that will be equal to 3 grams per gram. So we are going to calculate some number like this. So how much, what's the mass of paracetamol transferred from the solution to the seed particles per in that unit volume of the in that unit volume of the solution. Yes. So that's what you have to do. So how to get that value? So this is a simple mass balance equation. So anyway, I gave the formula, so you don't have to worry. So what is this? So QE is nothing but this value, the amount of mass which we are transferring onto unit mass of seed. So this is your initial concentration. Imagine if you start your experiment say with 100 kg and say after 5 minutes your solution concentration dropped to 95 kg, and if your volume is say 750 ml or it should be 0.75 liters, let's keep it in liters, 0.75 liters, because our concentration is expressed in grams per liter, so this is in 0.75 liters. Say we add a mass of 3 grams, so whatever the value you get, that one will be equal to gram of paracetamol divided by gram of your seeds. So this one will give some idea about the gram of paracetamol transferred from solution to your seed particles per gram of your seeds. So if, how do you call, if it's 10 gram per gram, which means you transfer 10 gram of paracetamol onto 1 gram of your seed particles. So that's the meaning of this. And why this unit? You see this concentration is expressed in grams per liter, multiplied by volume is expressed in liters, divided by mass of seeds is expressed in grams. Liter gets cancelled. So this is gram of your paracetamol. This is gram of your seeds. So that's the meaning of this. And in chemical engineering, this value, let's change the highlighter. This is nothing but your yield. If you want, we can call this crystal yield. So this one will give how many kilograms or grams of crystals you can get from that crystallizer. So this will be your theoretical yield. Yeah, I think this is correct. Yes, this is correct. So what does that mean? Like, imagine like you, let's go back here. If you start from 100 grams per liter, and if your solubility concentration is 80 grams per liter, you take the difference, 100 minus 80, and then multiply by, imagine if you are performing all of your experiments in 1 liter solution, you just multiply it by 1. So which means the total mass that you can get is 100 minus 80, that will be 20, multiplied by 1, it will be equal to 20 gram of crystals. So that's the mass of crystals that you can crystallize inside the crystallizer. Yeah? So that's why we call it as yield. If the yield is equal to 100 gram, what it means, it's like you cannot crystallize more than 100 gram in the crystallizer at that particular time. Mhm. I think this is enough. And then this value Y crystal QE, okay, that we can come back to that later. For the moment, let's go to the next one. And then once you calculate this QE value, this value is easy to get. I gave you this value. What is your concentration at T is equal to 0? That will be, if you go back to this table, you have time at the 0th minute, you will have some concentration, say 76 grams per liter. That will be the value of C0 at time T equal to 0. And then C will be like concentration at any time T. And V is your reactor volume, which is 750 ml. You have to convert it into liters, and then you have to calculate the mass of the seeds. I already said seed loading is 50%. From that, you have to calculate the mass of your seeds. And once you calculate this QE value, you have to fit. You have to fit the data T versus QE. So QE is nothing but the amount of mass transferred onto unit mass of seed. This is really, really important. Yeah, this is the easiest way to model crystal growth kinetics. And industries, they always look for some models that allows them to model the entire kinetics. Say like if you have some data like this time versus QE, if this is your experimentally obtained data, industry people, they like to use some equation that will allow us to predict this trend, how QE changes with time t. So for this exercise, you are going to use this one equation. This might sound very tricky. So what I do is like I will explain now in this video, and then I will try to show you in the Excel how to do these calculations for maybe for few data points, and then you can do the rest of the calculations by yourself. So once you calculate QE using this equation, let me write that equation. What is this QE? I think I messed up the page. C at T equal to 0 minus C. This is concentration at any time multiplied by volume of your reactor volume divided by mass of your seeds. So this equation is very difficult to solve. It looks a bit complex. So what I did is I linearized this expression. So what I did is like you take this equation and then you take the inverse 1 by QE. Numerator will go to denominator and denominator will comes to numerator. So that's what is I did here. 1 by QE. This is the numerator, this is your denominator. Now we can expand this equation. 1 by QE is equal to 1 divided by this value plus KV divided by this value, which is here. And then what I did is like I multiplied by T on both sides. So it will be like T by QE, and then I added T, I added T, another T here, and then so if you T in the denominator, T in the numerator, we can cancel them. So this T get cancelled, and then this T and this T get cancelled. So you will eventually end up with this expression. So T by, just add the remaining parameters, T by QE. Here T and T get cancelled, so just 1 by this value kV, k suffix v, q suffix m to the raised to the power of 2 plus this value T by qm, T by qm. So these are, if you look at this one look like a linear expression. Y is equal to mx plus c, where y is T by qe, and where x is just your T value, and your m value is nothing but 1 by qm. This one, and your whole intercept is this value 1 divided by k suffix v qm raised to the power of 2. So that's your c value. So what we get is like if we plot T by q, so which is your y, and then your x is nothing but T, you will get some data like this. All you need is to draw the best fit line, and from the best fit line according to this equation, so I wrote it here. So your slope should give 1 by qm, and your intercept here, that should be equal to 1 divided by kvqm squared. I hope you all know these equations, like y is equal to mx plus c. If you plot y versus x, your slope will be m, your intercept will be equal to c. So that's what I did here. So you have this linear expression. So this is your y, this is your c, 1 by qm, t is your x, and 1 by qm, that's your m. I hope you all follow this one. This may sound a bit tricky, but we have to go bit by bit, very slow. I will try to how to solve just in the I will use the notebook to show how to do the calculations, and then I will use Panaptau, and then I will try to record my screen. I will try to show you using Excel how to perform the calculations. Yeah? So that way you might find it easier. And you have to do all these calculations, because in exam you will have some questions based on whatever the calculations that you are doing for your experiments. So I might give some values, and then I will ask you to calculate what's the amount of or what's the mass of your solute or your crystallizing compound transferred into the seeds. So you have to tell to me. So from the plot, T by QE versus T, from the slope value, slope is equal to 1 by QM. So therefore QM will be equal to 1 by slope. And then your intercept is equal to 1 by KVQM square. So your intercept will be equal to this whole parameter in that expression. And then KV is equal to 1 divided by QM square multiplied by intercept. So KV, that's my name, K Vasant, because I derived this. This is my own model developed during my PhD. So KV is like 1 by QM square multiplied by intercept. And this model is very accurate in modeling the crystal growth. That's why I gave you. It predicts with near 100% accuracy. And these are the units. Whenever we talk about calculations or problem solving, units are important. Yeah, with if you don't care about units, there is no meaning of doing any calculations. Yeah, so every you should pay attention to the units, especially crystallization. You should pay attention to what's how the solubility units are expressed, how the concentration units are expressed, and how the this QU parameter is expressed, and then what will be the units of the constants and so on. But for this tutorial, for this lab, I'm going to tell what are the units. So just don't forget this one. So your units of QM, it will be exactly same of QE. So it will be gram of paracetamol divided by gram of seeds, and then the unit of KV will be equal to exactly the inverse. Oh, sorry, no, not gram of solvent. KV unit will be exactly inverse of the concentration of your your solute. So which means liter of solvent divided by gram of paracetamol dot minutes. So just don't forget these units. Units are really important. And then this is your final graph that you need to put it in your report. I think this is figure 5. So you plot T by Q, put the units. T will be in minutes. So Q is expressed in grams of paracetamol dot grams of solvent. Sorry, grams of seeds. Grams of seeds. Time will be expressed in terms of minutes. So this will be your graph. So this will be your 50% seeds, and this will be your 80% seeds. Or maybe the other way around. You have to plot and tell to me. So maybe, yeah, no. This should be your 80% seeds, and the one in the top, that should be equal to 50% seeds. You can check that by plotting in the graph or using Excel. And if any of you, if you don't know to use Excel, there is no way you can solve this problem. Yeah, because I'm going to give you data like this. As I said in the YouTube video, this experiment is very slow, so you will have like 24-hour data starting from 0th minute to maybe nearly 10 hours. So I recorded for every 2 minutes. So every 1 hour you have 30 data points. So 30 multiplied by 10. So you will have 300 data points. You cannot do it by hand. So you must use Excel. Excel, or if you know to use MATLAB, you can do it in MATLAB, but Excel is is much more easier. So this is the last plot you have to plot, and then you have to check the R square values. If the R square values are 0.99, which means your model is good. Okay, and once you finish this one, you take the slope and the intercept, you take the slope and the intercept, and then you have to go back to here. Use this formula. From intercept you can get your kV value, and then from the slope you can get your QM value. So you have to calculate QM, and then you have to calculate kV, and then you make a table like seed loading, your first experiment which is 50%, second experiment which is 80%, and then what is your kV value, the calculated kV value, and then what is the calculated QM value, and then you have to add one more value, or maybe let's ignore this one. So probably you might struggle if you do not have mathematics background. Normally V initial means initial crystallization rate. Let's forget this one, we don't have to include. I showed you how to get the initial reaction crystallization rate. We don't need it. Yeah, let's strike it out. So you have you have 5 figures for your report. So you have to calculate time versus supersaturation ratio. Then you have to calculate delta C, which is nothing but C minus C star. And then what else? You have to calculate QE, which is nothing but C at T equal to 0 minus C multiplied by volume by mass of seeds. So how to get your supersaturation ratio? So S is nothing but C by C star. If we go back to the question, if we come back here, I gave the value of C star. So your C star for paracetamol at 20 degrees centigrade is 108.18, I think, yeah? Gram of paracetamol in or per kg of IPA. So if you look at the instructions, what I said, you have to express this delta C in grams per liter, yeah. And then I said your reactor volume is 750 ml, so it's better to keep. So just to maintain consistency, all of you use the same concentration. You should express concentration in terms of grams per liter. Supersaturation ratio, this one have no units because C by C star is grams per liter divided by grams per liter. So all the unit gets cancelled. Your temperature should be expressed in terms of degrees centigrade, and time should be expressed in terms of minutes. Minutes or seconds, whatever you like. So if you look at this one, you have a solubility concentration of 108.18 gram of paracetamol divided by kg of IPA. So we need to convert this into grams per liter. How to do that? say C star, that's equal to 108.18 gram of paracetamol divided by kg of IPA. So we need to convert this C star in terms of grams per liter. So what you are going to learn now is like unit conversions. In crystallization, this is very important because in industry, sometimes they do it in 10 ml reactor, sometimes they do it in 100 ml reactor before they are thinking to use the industrial scale reactor. They will do a lot of preliminary experiments. Crystallization is a really stochastic process, and a lot of things needs to be optimized. So in industry, normally before going for the production, before going to start anything at production scale, they will try to scale the whole process in small scale reactors, starting from 10 milliliter, 100, and then they will go to 1 liter, they will go to 10 liter. Then finally, if everything is fine, they might go to industrial scale reactor. Yeah. So that's why unit conversions are really important. And solubility is a time consuming job to to get it to get those values experimentally. And normally, mm, including myself and many industry people, they take the solubility from the literature, and everyone use or express solubility in different form. Like I like to express in terms of grams per liter. So grams of our our solute per liter of solvent. Few people, they don't like these simple terminologies, they like to complicate, so they express in terms of grams of solute per kg of solvent. That's what I gave you, some numbers. This is, if you look at here, C star, this is expressed in grams of paracetamol per kilogram of IPA. I really hate people who are using this type of units, but for some reason they keep using it, and which means we need to convert them into grams per liter. So we need to convert our solubility concentration into grams per liter, and then I will give you the data in concentration, time versus concentration. Sorry, concentration expressed in terms of grams per liter. So hope up until this point is okay. Even if you feel it difficult, even if you found this as I don't know how to say, you may think it's slightly difficult because crystallization, the process is easy, but the calculations is always tough. Yeah, tough. And if you don't have expertise, or if you, how do you call, like if you don't practice in home, you will lose the track, and you have a very high chance of doing some mistakes, especially with units. So we will go very slowly, one by one. I will show you how to do the calculations one by one, like how to convert these grams of gram per kg into grams per liter, something like this one. And then we will calculate our supersaturation ratio, and then we will calculate our QE values. Then I will show you how to plot, and then how to get the kinetic constants. Yeah? And then you really need to do some a bit of I know you are the third year pharmaceutical chemistry, and final year chemical engineering students, and grad deep chemical engineering students. Yeah, so I have a mixed class, so I expect something minimum. Yeah, you have some data like supersaturation versus time. Just assume it starts from 1 to 1.2. So this is like 80% loading, this is like 50% loading. You are learning a lot in crystallization. Yeah, crystallization is a very tough topic, and I think you won't study this particular topic in any other modules. And for chemical engineers who were sitting in this class, remember that, like, you are not going to study crystallization in any other modules. Yeah, I know there is a crystallization in one of the modules, but we removed it. So this is the only module where you have a chance to learn about crystallization, so that's why I'm covering it in a bit more detailed. And for pharmaceutical chemistry students, they must know, there is no way to ignore this topic. There are few topics pharmaceutical chemistry students shouldn't ignore: crystallization, and then chromatographic separations, and then adsorption. So these three topics they are going to use again and again. And okay, adsorption, you may not use it, but you are going to use the adsorption principles, like even for example column chromatography. If you don't know anything about adsorption, forget how the chromatographic separation technique works. Yeah, so everything is connected bit by bit. And you will also use liquid extraction. That's especially for when you are going to, like, how do you call, like separate vitamins or antibiotics, then you must know how the liquid extraction works. Yeah, so this is not a bad module. It might look bit tough and it might look bit lengthy, but I think we are doing fine. I already got few comments from students that videos are really long, and it's slightly intimidating. Yeah, it's not my intention. I just want you to learn this topic, and you should know this topic. There are few, I repeat this again and again: crystallization is extremely an important unit operations. Yeah, so it will help you to make a product from 60% purity to 100% purity. Crystallization can do that, and that's why company industry people, they really love. Yeah, so if and what we are covering at the moment in crystallization is what exactly industry people are dealing with. Yeah, if I am you, if you really manage to learn everything whatever I'm going to teach in crystallization field, I think you can safely put it in the CV that I have a significant expertise in the field of crystallization. And also pat you are already, you can add it in your CV. You can put you gain practical experience with pat, because whatever you saw in the YouTube, you are going to do the same in the lab. The only thing is, you are not standing next to me in the lab. Other than that, you are going to do exactly same. If you have a laboratory access, you are going to do whatever I did. Yeah, so you can add that in your CV. And crystallization is a must topic. Yeah? I have few friends in different pharma companies, and they are using this technique again and again. So so don't ignore this topic. It may sound bit tougher. You may find it hard, especially because it involves a lot of unit conversions and so on, and that's completely normal. As I said, like solubility. I don't know, for some reason every research group in this world, they follow different units. Like some guy express gram per kilogram, some guy express gram of your API per gram of solvent. Some people, they express grams per liter. Some people express something completely crazy units. Yeah, so and you must know how to convert those data, or and and how to convert the units especially. Yeah, so that's the real deal. If you so the key difference between uh, understanding the topic, but understanding the topic is really easy. Like if you read some good textbook, or if you listen to this lecture or any other lectures which is available in YouTube or from any other resources, you are going to gain the knowledge, but there are few things that you should practice, like you should sit in home, try to solve the problem, or whatever I'm saying now, try to repeat the calculations, take a pen and a paper. If I'm going to convert something like gram of paracetamol to kilogram of IPA, try to do that by yourself. Use the calculator or use the Excel. Anyway, your exam is going to be open book exam, so you can use Excel. You are going to sit in front of computer, so it's going to save a lot of time for you. So try to do that, yeah. And if you are using Excel, save the file, because and then give some file, how to say, like fill every details in the Excel worksheet. Save the your save your Excel worksheet. So in case in the final exam, if I ask some question, you can open that Excel worksheet, you can use it as a template, put some numbers, you can get your answers very easily, no? So I'm really sorry for taking these lectures bit bit longer, yeah, because crystallization is really tough topic, believe me. And let's go back to the calculations, yeah? Sorry for giving this, I don't know, it's advice or tips. There are few things we have to learn. This is the right time to learn these topics. And you are not learning anything like a textbook knowledge, so these are something what we do in the lab in the industry, and also in our lab. So whatever we are doing in the lab, exactly the industry people, they are going to repeat the same thing, in fact we do it in a more sophisticated way, we do it in more precise way, yeah? So so try to, I don't know how to say, I kindly request to 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 bear with me, like I know I'm going very lengthy, but you will understand a lot at the end of this lecture. So let's begin with what's mean by 50% seed loading. So if you check the SOP of any industries, they will have this type of words like 3% seed loading. In fact, in industries, mostly they do the experiments, perform the crystal growth experiments with the 3% seed loading. Rarely they go to 50% or 80% seed loading. So what do I mean by 50 or 80% seed loading? So let's start from the solubility value. The solubility value is 108.18 gram of paracetamol per kilogram of IPA.